All right, in this video, I want to go over the central limit theorem. Okay, so hopefully up to now, you're pretty comfortable with finding probabilities of normal distributions. Well, what happens if the distribution is normal? Are we able to find the probabilities? Well, in general, the answer is no. However, if we apply something called the central limit theorem for means, we are able to find probabilities. And so the central limit theorem for means is based off of the distribution of sample means. And so what that means is that you're collecting a bunch of sample means, meaning you have a bunch of different samples, and for each of those samples, you're going to collect the mean. The distribution is then formed from each sample mean that you collected. Well, it turns out that if the sample size that you're using, if it's big enough, then that distribution of sample means actually becomes normal. We say approximately normal. And so the key here is that the sample size should be at least 30. And what that means to us, that means that your sample size, it needs to be at least 30 in order for us to say that the distribution of sample means is approximately normal, and therefore we can find related probabilities. Okay, so the central limit theorem says this. If your sample size is large enough, remember for us that means that n has to be greater than or equal to 30. If our sample size is big enough, then the distribution of the sample means becomes approximately normal. It becomes normal with the mean that is the same as the distribution. And you're going to see me use this notation a lot throughout this video. Mu x bar. And what that means is that that's the mean of our sample distribution of sample means. Well, it turns out that the mean of those, that distribution of sample means is the same thing as the population mean. Okay, so the normal distribution has the same mean as the original distribution. But the standard deviation that we use for the sample distribution is the original standard population standard deviation divided by the square root of your sample size. So look, in just layman terms, what this means is that as we go to find our probabilities, if you remember, we use normal CDF, we need four things. We need a lower bound, an upper bound, a mean, and a standard deviation. Well, now that we're going to be finding, probabilities of distributions that may be unknown, as long as the sample size is large enough, we can use a mean that's the same as mu, and we can use a standard deviation, which will be sigma over the square root of n. And sometimes the standard deviation is also referred to as the standard error. You may hear that as well in different lectures or different in different books. All right, and so here in this slide, they're just telling us that, look, the mean of the sampling distribution is, they're using that notation mu x bar. I wish they would put a bar over that. Let me see if I can do it for them. Put a bar over that x. And the standard deviation is sigma x bar. And then they're telling you that the, once again, mu x bar is equal to the mean, sigma x bar is equal to the standard deviation divided by the square root of n. Okay, so just keep that in mind. Here we go. We have an unknown distribution is created by the test scores of a nationwide standardized test. The distribution has a mean of 90 and a standard deviation of 15. A sample size of n equals 35 was randomly drawn from a population. Using the central limit theorem for means, what is the mean and the standard deviation for the sample mean distribution? Okay, so all they want us to do here is find the mean and the standard deviation of the sample mean distribution. Well, first of all, we notice our sample size is big enough. Our sample size is 35. So that means we can apply the central limit theorem. And the central limit theorem tells us that if your n is bigger than 30 for sample means, mu x bar is equal to mu, which is the population mean. And they tell us that we have the distribution has a mean of 90. So that means that the mean of our sample distribution will be 90. Okay? The standard deviation, on the other hand, of the sampling distribution is the population standard deviation they give us divided by the square root of n. So you just don't use that standard deviation, you have to divide it by the square root of your sample size. In our case, they tell us that we have a standard deviation of 15, so we need to take 15 and divide it by the square root of n, our sample size. Our sample size is 35. Okay. I'm going to load up my calculator and we are going to calculate what that value is. Okay. So I'm going to take 15, where's my mouse, 15, I'm going to divide it by the square root of 35. Enter into, let's say, 2 decimal places, I got a 2.54. So this is approximately 2.54. There you have it. That's your mean, and that is your standard deviation of the sample mean distribution. All right, similar question here. So we have an unknown distribution. And this is the birth weight of males in a certain country. The distribution has a mean of 7.8 pounds and a standard deviation of 1.2 pounds. We've got a sample with size n equals 150. So that means right there we can apply the central limit theorem for sample means. We are big enough. So the size of 150 was randomly drawn from the population. Using the central limit theorem for means, what is the mean and standard deviation for the sample mean distribution? Okay. Mu x bar, the mean of the sample mean distribution, is the same thing as the population mean, which they told us this distribution has a mean of 7.8 pounds. Okay, so the mean is the same thing as the population mean, but the standard deviation is not the same thing as the standard deviation that they give us. It is the given population standard deviation divided by the square root of n. So in our case, we're going to take 1.2 pounds and we're going to divide it by the square root of 150. That's because our sample size is 150. Okay, I'm going to throw this in the calculator. So we have, let me clear that out. We have 1.2 divided by the square root of 150. All right, there we go to, let's say, 3 decimal places. We have a 0.098. 0.098. And there we go. That's our mean and our standard deviation, which eventually is going to help us find a probability, but all they're asking for here is just the mean and the standard deviation. Okay, so now what we're getting into is how do we find now probabilities of these unknown distributions applying the central limit theorem. So way back in the day before they had calculators, what we would do is we would calculate the z-score, but we would use the mean and the standard deviation of from the central limit theorem. And then once we have the z-score, we would use those z-tables. Okay, well now we have our calculator, so we can skip the whole z-table step and we can go straight to our calculator. Okay, and they're just showing you here. Remember we said the mean is the same thing as the population mean, and they're reminding you that your standard deviation is the standard deviation divided by the square root of n. They're just filling that into the z-score formula. We won't have to do that because we will use the calculator. Here we go. An unknown population distribution has a mean of 90 and a standard deviation of 15. A sample size of 31 is drawn randomly from the population. What is the probability that the sample mean is between 85 and 92? So we're trying to figure out the probability that the sample mean is between 85 and 92. So what that means is we're trying to figure out, well, probability means normal CDF. Okay, so we're going to use normal CDF. Okay, I'm going to use normal CDF. And in the last video, if you haven't watched that video, please go back and watch it. Remember, there was 4 things that we needed for normal CDF. We need a lower bound on our values. In this case, if our X bar is going between 85 and 92, that means that our lower bound must be 85. And our upper bound has to be 92. Okay. We also need a mean for the normal CDF. So our mean will be, now we apply the central limit theorem. And the mean of the sample mean distribution is the same thing as the population mean. And it tells us the population distribution has a mean of 90. So our mean is 90. And the standard deviation that we're going to use, as you can tell by now, is not just the 15. Okay. It's going to be 15 divided by the square root of n. And n is 31. All right. And that is because we are applying the central limit theorem. Okay. Whenever they say find the probability of a sample mean, you got to use the CLT, the central limit theorem. Now we're going to put all this information into our calculator, just like we did in the last video. So let's pull that on up. Okay, let's clear it out. Second vars is how we pull up normal CDF. Go down to number 2. And we are ready. Our lower bound, it was 85, I believe. Let me double check. Yes, it was 85. So the lower bound was 85. The upper bound was 92. Okay. What was that mean? That mean was 90, I believe. And let's see here. What was the standard deviation? So the standard deviation is 15 divided by the square root of 31. Okay. And yes, you guys know the issues with rounding. Put in 15 divided by the square root of 31. Don't calculate that standard deviation beforehand. Just go ahead and throw it all in there. Let's paste it. Once again, if your calculator is not updated, remember you have to put those 4 values in that order: lower, upper, mean, standard deviation, comma separated. Comma separated. We hit enter, and there we go. To 3 decimal places, we get a probability of 0.739. So this answer is a 0.739. All right, let's keep it moving. Another example here. Unknown distribution. We're talking about the birth weight of males in a certain country again. And so the distribution of the mean, the distribution has a mean of 7.8 pounds, standard deviation of 1.2 pounds. We got a sample size of 150. So that means central limit theorem is in play. What is the probability that the sample mean is less than 8 pounds? Okay, so what I like to do with this one is I like to go ahead and take that last statement. What is the probability the sample mean is less than 8 pounds? And I like to write that in my probability notation. So that's the probability that X bar is less than 8 pounds. Okay, I like seeing that because now it's going to help me when it comes to my lower and uppers. Okay, in fact, what is our lower bound? So we're talking about being less than 8, right? And so that means that our lower bound is a negative 1e99. So once again, go back to the last video if you forgot what that meant. That means a negative infinity for us. The upper bound is going to be 8, right? Because we're stopping at that 8. That's our largest value. And our mean will be the same thing as the population mean. So the distribution has a mean of 7.8 pounds. So that's our mean. And then our standard deviation will be the 1.2 pounds divided by the square root of our sample size, which is 150. Okay, so here we go. Calculator time. Let's clear it out. Second vars, normal CDF. Lower bound was a negative 1 E, where you at? There's the E, 99. Upper bound was 8. What was that mean? The mean was 7.8. And I believe the standard deviation was 1.2 divided by, oh, I forgot my divided by. Okay, 1.2 divided by the square root of 150. Now let's close that up. All right, enter, paste to the home screen, and we get a probability of 0.979. Probability of 0.979. So that means it's very likely that we're going to get a male birth weight that's less than 8 pounds. Okay, that's really, really close to 100%. I mean, it's almost certain. Okay, so actually that's it for us. So hopefully this will help you guys out with the homework when it comes to applying central limit theorems and using that central limit theorem to calculate probabilities of unknown distributions.